Okay, so consider a general reaction. We have our A going to B, right? Notice, by the way, in these reactions or equilibriums, the products and reactants can always be swapped, right? Because it's an equilibrium. Anyways, so we have an enzyme for this reaction. Our delta G naught prime of the reaction, we're given this number here, and calculate the equilibrium constant for the reaction at 25 degrees Celsius. So we're just going to use that same formula we just used in the other video, right? And so I go ahead and pump this up so I can get the formula without having to do some searching. And there's our formula, right? Our delta G naught prime equals negative R times T natural log of KEQ. Okay. And so we substitute R in, which is a constant. Our T, well, it needs to be in Kelvin, but it's that 273 plus the 25 degrees Celsius we were given, right? So 298 Kelvin. Okay. And so then we substitute the rest of the stuff in. You could either plug the numbers in and solve, or you can rearrange first if you would like. Okay? This is what it would be if you rearranged it. You get your KEQ out. To undo a natural log, you would have to take e to the power of. So you take e to the power of what's on the left side after you finish rearranging. So for example, you divide over negative RT, right? You take e to the power of both sides, so you get e to the power of delta G over negative RT, right? And that would give you KEQ. Is everybody okay so far? That's just the rearrangement. We plug our numbers in. So we do that 4.78 times 10 to the negative third we were given, right? Make sure your units match. Notice this is times 10 to the third, right? Because we need to have it in joules, because our R is in joules. You can go into kilojoules too. It doesn't matter. You just need to have the same, right? Or else you won't cancel. Okay, and then that R is down here times the 298 Kelvin down here. Okay? You will get a negative number here. It typically is not a huge number, but you know, it can have, it's not a huge number typically. Okay? So it'll be e to the power of 1.929. So negative, by the way, because the delta G was negative, right? Okay, and we solve that, e to the power of, we get 6.88, and that would be our KEQ, right? And then we would put that in, 6.88. Okay. So what is the delta G for the reaction at body temperature? If the concentration of A is 1.8 and the concentration of B is 0.75. Uh-oh. Oh my goodness. What's going on there? So we pretty much use that same formula again, right? But all of a sudden now, we got to do a little bit, we have to use what that formula was derived from, right? So does anybody remember why that formula didn't have a delta G, it just had a delta G naught? What's delta G for equilibrium? Is an equilibrium spontaneous in either direction? No, it's not, right? Or another way of putting it is it's spontaneous in both directions. Okay? Well, where would that happen? That would be delta G equals 0, right? So this is actually the derived formula where delta G equals 0 from this one right here, right? Okay. And notice that's products of reactants. When we're not at equilibrium, this would be called a Q, right? The reaction quotient. When we're at equilibrium, that would be a K, right? Which is the reaction equilibrium constant. Okay, so here's the original formula. We're going to be finding delta G now. We have our delta G naught prime. R and T, well, R's constant. T is going to be based on that, what was it, 35 degrees Celsius? So 273 plus the 35. And then we have the concentrations of B and A. Note, because the reaction is a 1-to-1 ratio, we don't have any powers in here, right? Okay, that is important, though in biochemistry, you pretty much always have it like that. It's very uncommon to not have 1-to-1 ratios. All right. So again, the T would be 310 Kelvin, right? That 37 degrees, I guess. And delta G would equal then, well, that's our number we were given at the beginning, the 4.78 kilojoules per mole, plus our R value right here. There's our Kelvin temperature. That's our natural log, B over A, concentrations, right? Okay, then we start solving. Note that we will have to convert this number right here into a kilojoules number. See that? We'll need to get these units the same. Be careful if you're not thinking things through at the beginning, that you carry your units through, okay? Because if you carry your units through, you won't mess up. All right. So we'll do this. You get that solved. You end up with a pretty big number because it's in joules. You convert that to kilojoules, and it'll end up as negative 2.26. Okay? So it would have been 260, right? And this right here, we'll just take it down. We don't do anything with it. We add those numbers together, which gives you a negative number, and our delta G ends up being negative 7.04, right? Kilojoules per mole. That's the units. There we go. They're over here. That's why we chose kilojoules, by the way. Anybody have any questions? No? Okay. Was anything unclear at all? Or?